Okay, so now to the discussion session. We already have a few questions that came up through the website, and I displayed them here. And the idea is now that we have our 3 invited speakers here that you've already heard, and we can ask them more questions about machine learning and material science. So I suggest we start with one of the questions that we have up here. So there was this one about the callback labeler that was about neural networks, right? That's something that how about this one? To which degree neural networks are interpretable? So we talked a lot about sort of and you did with the chemical space. Talk more about models that have a more direct physical interpretation. So maybe since you introduced neural networks yesterday first, maybe you can say a few words about it. We pass the mic around.
Thank you, and good morning also on my behalf. What a comfortable chair. Yeah, and coffee. I'm liking this workshop more and more every day. Interpretable. That, of course, is a very prominent question that is being discussed all the time in machine learning, interpretable or explainable AI and machine learning, and that like, let's say, more maybe outside physics, it has huge implications in terms of accountability. But we can't say that, we rejected your job application, your loan application, or we rejected your health services because the computer said so. We don't want to do that. Appeal to the computer just saying so. And that is also something we want to avoid doing in physics, I guess, to some extent. This is not sort of probably very realistic, but sort of to characterize or sort of make a caricature of the argument, we would say that we'll build the fusion reactor with this material because the computer said so. And then it blows up, and yeah. So we want to be able to interpret the model so that we could be critical about them. So that, I guess that's the motivation for the question, I would assume. About neural networks, they are probably among the least interpretable models. So most other kinds of, let's say, regression models or decision trees or probabilistic models of some kinds are probably more interpretable. But so I guess the answer is not very. They're not. Was that the question? How to which degree? Okay, so to low degree. That's my answer. But then again, often we want not to interpret them as much as to be able to rely on them. And I guess what we've been doing is trying to have the networks reliable so that they would, or we would know when they are reliable or when not. And we were especially working on methods that associate uncertainty or like error estimates in the predictions. And that goes a long way in terms of solving some of the problems, but not all, I guess.
So I think this is a very deep question, and it's difficult to find a good answer to this. But so I would say maybe there should not be a specific focus on neural networks here, because other models are also difficult to interpret. So in a sense, a network just implements a function, but potentially in millions of parameters. And so the question is, what do you mean by interpretable? So mathematically, this is perfectly interpretable. It's a function in, say, 10 million parameters. You can write it down. So every detail of this function is specified. So there is no degree of fuzziness or something. So, but typically we refer to interpretability as something that we can understand, or we think we can understand, but it's, this is not very clearly defined. So I think it's very difficult for me to give a good answer to that. So you might, because it's not even for me, it's not even clear what you mean by how interpretable is a function. So do you mean how precisely you can predict the outcome, or what is your understanding of the input space or the importance of features in the input space? I mean, yes, all these are important questions, but I think it's somehow, I think you have to better formalize this question, what do you really mean? So interpretability can be many different things, and it's not so clear for me.
Yeah, could you add a Bayesian inference perspective on this?
Sure.
If you generalize from neural networks too.
I agree.
Into them.
Degree of interpretability is low compared to other classes of model, and I also agree that we need to agree on what we mean by interpretability. To me, it boils down to understanding why this is a cat and this is a dog. Something not easy to do. Neural networks. But on top of interpretability, what I would add is another feature that neural networks do not have, which is the possibility to study the effect of interventions. So as an advocate of statistical models, relative to machine learning type of models, I know that if I write an equation like a regression type of model, I can say, okay, what happens if I increase or decrease the value of this variable? What happens if I intervene in the phenomenon that I want to study with this or that? So what would be the effect of intervention? This is something you cannot study. But I certainly agree that it's a function with millions of parameters, and to that extent it is. From a more broad perspective, so far you can see neural network as an instance of Bayesian non-parametric setting. You can try to shade some light on, rather than interpretability, the notion of attaching some measure of uncertainty to the predictions that come out. And certainly reliability is important, and we are reliable if you can measure the uncertainty of whatever prediction. So efforts in that direction are really.
Okay, we have another question that is receiving a lot of votes, and that has to do with the descriptors. And this is then, of course, the input to the machine learning methods. So the question is, are there descriptors that work better for certain classes of materials? Or here the question specifies more into different types of solids, but then you raised this, Volker, also for molecules, right? When you discussed, for instance, how in latent space it is important that distances in latent space are also informative of distances in real physical space. So if you think about descriptors now, is there something that you think, in your opinion, the community needs to still do on working on the input to a machine learning?
Well, I'm absolutely no expert on this. So, but my understanding is that there are a couple of very good descriptors around, and I think from a science viewpoint, it's pretty clear what kind of invariances should be captured by descriptors, and these are the classical geometrical invariances. These have been studied in fields like computer vision for decades. So basically, I think we know how to incorporate these invariances in descriptors. In the end, it's just integration over the orthogonal group, and you can do this by developing your functions in Fourier or wavelet space or whatever. So I think we know what, in principle, how to do is this, but of course there might be some new and interesting tricks how to speed up the computation or whatever. So I don't think this has ended somewhere, but I think in principle we know what we would like to have in our descriptor.
How much should we sort of influence the problem by designing, putting certain features in the descriptor that we think will work well? I think that's the prior knowledge versus influencing the outcome trade-off?
I'm not sure I can give a good answer to this. So
You chose a particular descriptor, right, for your problem?
Yeah, so first of all, I'm happy that I didn't have to answer this question first, because I was kind of running blank on ideas. But I think these comments already inspired some at least some things that hopefully are related. Namely, that in computer vision, especially, so maybe I'll sort of pick up from there. So in computer vision, you might be aware that it used to be the paradigm used to be based on so-called invariant features, and facial recognition used to be really so that was the dominant paradigm, that people would take an image and then construct these features that you'd expect to be invariant with respect to lighting conditions or the perspective to the object and so on. And you would then extract that kind of invariant representation from your images and then use that as the starting point of your machine learning pipeline. And then there's been this big kind of transition, and at least a lot of talk about the possibility of deep learning and neural networks to operate on the raw pixel data. So you just put in the images, and the idea is that the neural networks, the first layers, would actually do this representation learning. I think at the moment there is a big conference called International Conference on Learning Representations, ICLR, and that's one of the main conferences in neural networks. And that I think is an example of the idea that the kind of boom and the success of deep learning, especially, it has a lot to do with the ability to learn suitable representations without kind of manually constructing features that are invariant. But then I guess the question there is that in the end, I think people believe that saying that you just put in whatever representation, raw data, pixels, or some sort of physical representation, and let the system learn all the representation. I think that is sort of taking it too far. And as Patrick said, that there is a chance for us to incorporate our subject matter expertise in encoding some features. So doing that kind of old-fashioned feature engineering work, and then sort of helping that bootstrap, so to speak, the system, so that it reduces the amount of data that is required. So I think so. This is a part of a bigger discussion that is going on in machine learning. How much do you want to just throw in, billions of data points, and let the system be smart, and the programmer can be kind of ignorant, at least, if not dumb, and then versus sort of trying to bring in the subject matter expertise. And as regards physics, I can not say where the kind of sweet spot, where the optimal point of operating is. It probably depends on the kind of problems they're studying. But I think that's an interesting discussion in the general case as well.
And Antonietta, how do you see the role of descriptors in Bayesian inference? Is it more difficult?
So let me take the statistical perspective rather than just Bayesian. So what in this community is called the descriptor, in statistical term, is a summary of the data. Okay? So in statistics, there's this notion of what is a sufficient statistics. That is a summary of the data that contains all the information that it's needed to make inference on whatever parameter we want to infer. Okay? So let me give you a specific example. If the data comes from a Gaussian distribution with a known variance, and you want to infer the population mean, then the sample mean is a sufficient statistic. So it captures all the information that is contained in the data that is needed to make inference on the parameter of interest. Then there's also this notion of minimal sufficient, because the entire sample is sufficient, but you want to summarize it in some sense and extract from the sample information that is needed and no more than what it's really needed to infer. So So the notion of a descriptor would translate, let me repeat this, into a statistics, a summary statistics, and we have this notion of a sufficient summary statistics. Now, in order to verify whether a descriptor is sufficient or not, you need a model. You need to specify the distribution of the data. And in some setting, this is not possible. In others, it is. So when it is possible, you can actually check whether a descriptor is sufficient or not for whatever parameter you are trying to infer. When this model is not well specified, or you cannot write down it explicitly, actually, so in order to check it, you need to write down the likelihood of the data, the distribution of the data, and if the distribution of the data, conditional on knowing this summary statistics, does not depend on the parameter anymore, then it means that that summary statistics really capture the information that is contained on the data to make inference on that parameter. If you cannot write down the likelihood or the model, then you cannot check whether this conditional distribution depends on this or does not depend on the data. So you cannot formally check whether a descriptor is sufficient or not. In those settings, you have to rely on knowledge domain information. So you want your descriptor to capture up to your knowledge domain the relevant information that is contained in the data to infer whatever parameter you're interested in. And this is what you actually do. So your descriptor capture some symmetry and invariance and so on that your knowledge domain tells you that are relevant features in the data that you want your inferential procedure to preserve. So I hope this at least puts whatever you're doing into maybe a different perspective, or like the statistical perspective, and might help.
Thank you. Well, if you keep the mic, there's a popular question now about inference or generative models and the inverse problem. So what do you see, what's the power of Bayesian methods on solving or addressing the inverse problem?
Very powerful. Let me say something, or let me repeat something that I said yesterday during my presentation. So I think generative models are very interesting because we can incorporate our knowledge domain expertise despite not needing to write down in closed form the model itself. Okay, so this is a big advantage. The disadvantage is that up to a few years ago, there were no principled there was no principled framework to infer or calibrate the parameter of those generative models. Now we have this very powerful family of likelihood-free inferential tools, of which ABC is just an instance. Okay, so the class is much broader. I told you about approximate Bayesian computation. There is a whole set of likelihood-free inferential framework. And those inferential framework basically learn about the likelihood using the feature of the model, which is the fact that it can be forward simulated. And within this community, my understanding is that many of your models have this feature, and you should take advantage of this. Moreover, if you rely on this feature of the model, you soon realize that you can make the model as complex as you wish, still being able to calibrate the model using these methodologies. So I really think this is a very, very powerful tool, and you should, I hope I've introduced this tool to this community, and you will make the effort to at least, read a little bit about it. The Wikipedia page is really well done. So look at it, and there is code besides ABC Pi. There is a lot of packages that do ABC. So it doesn't require a lot of effort in the coding. And it doesn't require a lot of effort in the understanding of the methodology. This is also what I find it's interesting about those methodology, is that they really fit the mind setting of a lot of scientists. Because when I go to ecologists and biologists or astrophysicists, and I tell, okay, this is what you should do, and they tell me, this is what we already do. But they do it by trial and error and in a non-automatic or principled way, but they really understand what's going on because that fits with their mind setting and what they are already doing. So I hope this idea sort of goes through this community as well, because it has really a lot of potentials.
So Volker, if we specify the question a bit more, the history of generative models actually goes far back. Why is it material science so slow to catch on? Is it because the material space is discrete, and therefore it's more difficult to do generative models?
Yeah, I think indeed the space is structured, and generative models over structured spaces are much more complicated than those over structured spaces. You need to have a output distribution that is able to capture this structure, and if the structure is something like strings, then the output distribution has to respect the grammar of your language. If in your smiles there is a parenthesis open, then there must be also a closing parenthesis, and so this is complicated. These are typically long-range interactions, and it is not so easy to implement that in a but then I'm not sure if our material science is very, very specific here. So I think generative models are not used so often, so honestly, in many applications. And I think the reason is, in my opinion, that it's sometimes difficult to come up with good schemes for sampling. Of course, we have all these Markov chain Monte Carlo sampling techniques, but they work to some degree, or they don't work, or you're not sure if they are working in practice. And there's a lot of uncertainty also typically involved with complex generative models. Also difficult in a sense. So I think, and this is to me one of the big advantages of these latent space variable models, because you have a compact representation, and you're probably much more confident about sampling taking place in that space compared to sampling taking place in a 10 million dimensional input space or something.
Teemu, anything to add on the generative models?
No, but I will add on something else, if you will.
Sure.
Just first, I'd like to check how many people here are physicists. And okay, how many are mathematicians? Okay, good. So then I can say what I was going to say. So I'm not sure which question you mentioned when you say generative models, but I was looking at the one on inverse problems, and I will maybe comment on that, if you will, again.
Very good.
So, since you're physicists, have you heard about somebody called Edwin Janes? How many of you have heard about Janes? Okay, something. So I guess maybe those of you who are diehard Bayesians probably have read his book on the logic of science. It's a brilliant, very provocative book. I really recommend it. Anyway, so what Janes, he was a physicist, but also he kind of worked a lot on also both the philosophy and the practice of Bayesian inference. And what he said about inverse problems' role in these kind of problems was that he was, as I said, he was a very provocative person, and he was saying that these people, mathematicians, who come up with inverse problems and say that they are good for solving problems as we are dealing with here, it's a misunderstanding, and they should call these are problems of inference, not inverse. And his point was that if you can invert sort of invert things in mathematics. But that usually, or that always requires that you have some fixed set of equations, and you know the, let's say, the outcome of the system or the transformation that you've done, and then maybe you have an inverse function that takes you back to the original domain from which you mapped into this outcome. But as soon as you don't know that value precisely, you have uncertainty and noise. Can't do that, right? There's no unique inversion of the system, and it becomes a problem, at least according to James, of inference. And these problems have been studied by statisticians for hundreds of years. And he was sort of saying that the mathematicians, they think that they've got something new, but as soon as you plug in uncertainty and noise into the system, there's little that these kind of inverse problems bring into the game that hasn't been studied in statistics for hundreds of years.
Yeah, you raised a good point, and there's actually a related question to that from the audience, and that is that about training, young scientists in this field. When I say this field, it's already the first problem, right? So your poll showed that there are mostly physicists in the audience, and probably very few from computer science, and we saw no mathematician. So you said a lot of these concepts are very well known in, say, statistics. So the question that comes from the audience is, what is actually a good way to train young scientists that come in from the material science side, physics, chemistry, maybe biology side, into a domain that is largely from computer science? And I think you all have come in from there. So what would you recommend? How should we how should we teach machine learning to specific domains like material science?
If I can very briefly start, I just recommend that unless people are still working on their degree, if they're working on their degree, then free to go to computer science departments, or feel free to come to us. We'll be happy to offer education. But if you're already kind of past your junior years in the university, then there's a lot of online education, and there's a lot of online courses that are very well designed, that are good introductions. You just, I think probably many people learn how to code to some extent with some systems in physics, and that's a good starting point. Then you just, you learn you take a couple online courses, and then you go into doing projects. So it's not only that you sit back and watch videos and you think you learn, but you have to kind of get your hands dirty with data, and that's also something that is really well supported by Kaggle. There's this site called Kaggle where they have online kind of machine learning kind of challenges or competitions where there's data, there's a problem, and you're supposed to work on that, and then you publish your results and see how well you did. And just, I think it's very easy to approach the field because it's all sort of open source tools. It's all like open science in the sense that people publish their methods, and then there is this open education. So it is probably a field where it's easier to go into than many other fields.
I can add that I'm involved in two panels exactly related to try to answer this question, not specifically for scientists, but more broadly, how should we train data scientists? So that's sufficiently broad. And this is a discussion that we are having inside the Institute of Mathematical Statistics, the largest society in the US, and therefore, more or less globally. And I'm involved as well in a panel discussion inside the International Society for Bayesian Analysis. So it's a timely question, and societies are asking that same question. It's not easy to answer. With the IMS, Institute of Mathematical Statistics, we are coming up with a white paper. Statisticians, probabilists, applied mathematicians, and mathematicians are really thinking about this question. And notions related to online resources is a point that we are discussing, for example. Creating shared platforms where videotaped lectures or discussions like you're doing will be made more publicly visible, because like you're doing, there are other, more and more conferences have at least key lectures or panel discussions that are taped and put online, but maybe people don't know where to look for what. And also the quality of the resources that you find online is not homogeneous. Even Wikipedia pages, they are very good for some topics, less good for others. So, and another key point is how to train young researchers in terms of leadership. So leadership, it's a broad term, and it's not like the formal training, learning about statistics, machine learning, computer science, and so on. And it's something very hard to train somebody on. Being able to lead and discuss when it will the time with colleagues and researchers how useful what you're doing is, or how useful a statistical approach is, uncertainty quantification, decision making, supporting decisions, and so on. So there's a general discussion going on at major statistical, mathematical, and Bayesian and non-Bayesian societies. So we'll come up with a white paper that sort of answers more broadly this question.
There's a related question, if I can stay with this point, and then that could be a wrap-up of our panel. And you mentioned this, the dissemination of knowledge, which is very traditional in the disciplines. In physics, material science is always done by papers and presentations, right? But what about sharing Jupyter notebooks, sharing pieces of code, making data available, actually generating data sets that the community can work with? What do you think about that?
Is also important. Well, it goes also in the direction of reproducibility of science and transparent. If you share your code, if you share your data, if you have some benchmark data sets that everybody can try their new methodologies on, having standards, benchmarks, quality settings, it's so important. Not only for learning, but also for and dissemination, but more broadly towards reproducibility of science, which is a key point. And we read more and more about published papers that or the p-value. Ballet actually talking about p-values. Maybe I shouldn't touch this, but again, IMS is a statement on p-values, and I invite all of you to read about values at this Institute of Mathematical Statistics statement about p-values and the pros and cons and alternatives to p-values. There are journals these days that don't publish anything that has p-values in there. I mean, this is an extreme. But be aware of this.
Volker, what would you say? Would you publish your generative model as a Jupyter notebook?
Without p-values. No, definitely. I think this idea of sharing code is very important, and the statistics community was very successful with R language, where basically publishes a code. And so I think we should establish a similar strategy in machine learning or in material sciences as well. However, I think this is not, a solution to anything. So this is something that you would like to have, but yes, having access to many data sets and code snippets doesn't really solve any important problem. And I also see the danger that this might bring us a bit away from the true underlying questions. So at some point it has become too easy to just do something without really understanding what you're doing. And this is, I think, a danger also for when I would like to come back to this question about how to train young scientists. I think in our field there's this big danger that you have access to so many different things and codes, and you don't really understand it, but they do something, and at some point you are happy with what they are doing, but you don't really understand what are the consequences and why does it work. And so I think it's also very important that we from time to time go back and try to understand the statistical principles, try to understand what is statistical inference about, and sometimes it's better to take a step back and try to understand the mathematics and this.
Okay, some final words, Teemu. And I think in computer science it's quite common to publish an algorithm and have very little in the actual paper, right?
Yes, so definitely I am in favor of publishing always the code, the data as far as possible. And but I think what Volker was referring to is the issue that if these tools are made extremely simple and easy to use, there is, and I share this concern that it's kind of not exactly, but it's almost like giving a loaded gun to a child. Like it's so easy to take some data and not understand the phenomenon that you're studying. I've seen that. I've worked in digital humanities, where there is a tendency for us, like engineering or computer scientist people, to go there and take some humanities or social science data and put it in and discover that, whatever causes something else, to just find correlations in the data and not understand that there are all kinds of biases underlying that the people in the field, like sociologists, are well aware of. And so that's maybe what, like, you were probably referring to by saying that putting all the code online doesn't solve a problem. I tend to think that it kind of is a part of the solution. Probably it doesn't solve the problem in itself, but I think I'm still in favor of making these tools easy to use. But they should also be, they should come up with these kind of disclaimers that just, we're not responsible if you if you shoot yourself, or if you go and publish some rubbish results with this easy to use tool. You should look, you should read the manuals and the instructions, and what are the assumptions that kind of can be broken and can destroy the validity of the analysis. And then I think that's the way to go forward. Just publish the code, but just don't say that this is a black box neural network that solves everything and you don't have to think.
Okay, so this is already the end of our time slot for the panel discussion here. So we have our next session coming up. So I'd like to thank all our three panelists. Yeah, thanks to the audience for participating.